All right, so we're in section 11.7. So we're going to talk about a new coordinate system today. I think cylindrical coordinates will become our second favorite coordinate system. And hopefully rectangular coordinates then follow to third place. And when we talk about spherical coordinates will be our favorite coordinate system. So cylindrical coordinates really are the extension of polar coordinates into three dimensions. So and a lot of people, I've heard them described a lot as polar coordinates with a z component. So what we're doing for cylindrical coordinates, yeah, that makes it sound great, doesn't it? So we're going to take our rectangular coordinate system and we're going to extend our radius, just like we did in polar coordinates. We're going to extend our radius out here. So this is going to be r. And this angle from the positive x-axis is theta. And if we set there's a final kind of a topical study guide there. If we extend this over to the x-axis and extend this down to over to the y-axis like so, this is going to be y and this is going to be x. And if we have a point up here, somewhere up above the xy plane, like so, might need to move my r, and we draw our dotted line up to that point here. So there's my point in space, there's r. We call this point in rectangular coordinates, our point is xyz. The length of this is z. And in cylindrical coordinates, we have our point r theta z. So r and theta, so if we project the point directly down onto the xy plane, the point that we have down here in the xy plane is given by r and theta, our polar coordinates, and then we just go up z units to our point there above the xy plane.
Mr. Beamer,
yes.
You wrote YYZ for the point.
Oh.
It's a good song.
I
don't think that's what you meant.
I'll claim that it was my technology. That's my claim. Yeah, YYZ for Rush. When I was, I had an internship once at the Hanford nuclear site in Washington State, and I used YYZ as my exit code from when I was writing programs. YYZ was like the way that you got out of it. And so anyway, cylindrical coordinates. Here are our cylindrical coordinates. Polar coordinates in the xy plane plus the z component. Our conversions from rectangular to cylindrical and vice versa are exactly like the ones we use for polar coordinates. We're just adding the z components. So our conversions, write it up here. These should be very, very familiar by now. If we're going to go from cylindrical to rectangular, we're going to say x equals r cosine theta, y equals r sine theta, just like that's just our polar coordinate conversions, and z equals z. We don't have to do anything with the z. And we say that the point 0, 0, 0 is the pole in cylindrical coordinates. And then if we're going the other direction, rectangular to cylindrical, r squared equals x squared plus y squared, and then tangent theta equals y over x, and z equals z. So all we're doing is adding a z component to polar coordinates. Cylindrical coordinates are nice. They're useful when we have some kind of surface that has symmetry, circular symmetry about an axis. That's when we'll use cylindrical coordinates. So if we have for example, a paraboloid, and its axis is the z-axis, it can be very, very nice to represent that paraboloid in cylindrical coordinates rather than in rectangular coordinates. It simplifies the expression of that paraboloid, and we'll look at a few of those today. So all I want to do is do a couple of conversions and look at some equations in cylindrical coordinates and do some conversions with those equations and talk about the surfaces represented in cylindrical coordinates. So the idea behind it really is polar coordinates in the xy plane, and then we add the z component for our distance above the xy plane. So questions before we move on? And like I said, I think cylindrical coordinates hopefully will become our second favorite coordinate systems. Spherical coordinates are just really nice. That's a really nice coordinate system. Okay. So we want to convert this point in cylindrical coordinates, our theta z. We have 3 pi over 2 negative 3 to rectangular coordinates. All right, so what do we want to do here? What do we want to work on first?
R. Let's do R.
R? Well, we have r, theta, and z. So we want to get x, y, and z. What's the easy one? Z.
Oh.
So we know it has to be z equals, there's our conversion, z equals negative 3. That one was easy. X equals 3 cosine 3 pi over 2 equals 0. Cosine of 3 pi over 2 is 0. And y equals 3 sine 3 pi over 2. I heard some of you, I think you were thinking of sine when we talked about cosine. This is going to give me negative 1 times 3, so we get negative 3. So our point is in rectangular, 0, negative 3, negative 3. Conversion of points are very easy, and it's exactly like we did with polar coordinates. Let's go the other way. Convert x, y, z equals -1, 1, 2 to cylindrical coordinates. All right, so what do we want to work on first here? Z, okay. Z equals 2. That's a 2, yes. Okay, what's next? R, okay. So R is going to be, we can do, R could be positive or negative. So we could say a plus or minus 1 squared plus 1 squared. So we get plus or minus the square root of 2. And let's look at our x and y coordinates. What quadrant are we in the xy plane here? Second, third, and fourth. So the x is negative, y is positive. So we're in the second quadrant in the xy plane. So that tells us where we need to find our theta. We need a second quadrant angle for theta. So to find theta, what are we going to do? What's our conversion? Tangent theta, right, equals -1/1. So we're doing the inverse tangent. Theta equals the inverse tangent of -1, and we need a second quadrant angle. So what's our second quadrant angle with a tangent of -1? Theta equals 3 pi over 4, and it could be some multiple of pi of that as well. And what's that? Period of tangent is pi. So we would adjust depending on where we were with this one. We would use a positive or negative radius. So we'd have to make sure we use the negative radius with the appropriate angle. But if we wanted to keep it a positive radius, then we would add 2 pi. You're right. All right, so we have two choices for r and infinite choices for theta. So we could write we'll write two representations for the one point. So our point is, we could write lots of, we talked about how polar coordinates weren't unique. So point could be square root of 2, 3 pi over 4, 2. That would be one representation of that. Or we could say negative square root of 2, 7 pi over 4, 2. So we just need to make sure we adjust so we're in the proper quadrant. Those are two possibilities for that point. Questions? Points representing points in cylindrical coordinates, kind of interesting. It gets much more interesting when we start talking about surfaces. So we want to represent a couple of surfaces, or we want to go from rectangular to cylindrical with surfaces, and then talk about what kind of surface we have. And we'll go the other direction as well. So let's look at a surface. X squared plus y squared equals 4z squared. We want this two cylindrical coordinates. Well, this one's easy. X squared plus y squared is r squared. And z equals z. So r squared equals 4z squared. So that's our surface in cylindrical coordinates. What is this surface? If we let x equal 0, we get y squared equals 4z squared, or y equals plus or minus 2z. So what is that? What is that in the yz plane? That's a line. And if y equals 0, we get x equals plus or minus 2z. So we get a line in the xz plane. So that's a cone. So if we sketch out a quick graph, we get, in the yz plane, we get lines. In the xz plane, we get a line, and we can extend down below here as well. Parallel to the z-axis, so if z is a constant, we get x squared plus y squared equals a constant, which is what kind of shape? X squared plus y squared equals a constant? That's a circle. So parallel to the xy plane, we get circles. So we get this cone. So this is a double naped cone. It has two napes, that's right. Oops. So the expression of a cone in cylindrical coordinates, a cone has circular symmetry about the z-axis. A little nicer expression for a cone. We get rid of that x squared, y squared. We just have an r squared. All right, let's go the other direction with one. R cosine, this one's a nice one. R squared cosine 2 theta plus z squared plus 1 equals 0. We want to write that in rectangular coordinates. And the nice thing about cylindrical coordinates and spherical coordinates is we get to start using trigonometry again. And it's always nice when we get to use trigonometry. All right, so what are we going to do here? What's giving us a problem? The cosine 2 theta. So we want a nice identity, hopefully, for cosine 2 theta. Cosine 2 theta equals cosine squared theta minus sine squared theta. That looks kind of nice because now we have these combinations of r squared and cosine squared and r squared and sine squared. So we get, if I distribute, I get r squared cosine squared theta minus r squared sine squared theta plus z squared plus 1 equals 0. This is starting to look nice. R squared cosine squared theta is x squared minus r squared sine squared theta is y squared plus z squared, and I'm going to say that equals negative 1. And then our standard form has a positive number on this side, so I would write minus x squared plus y squared minus z squared equals 1. And do we remember what that surface is? We talked about it yesterday. We have two minus signs.
Hyperboloid of two sheets.
Hyperboloid of two sheets. So we can have a hyperboloid of one sheet where we have a connected hyperbolic surface, and we can have a hyperboloid of two sheets where the two parts are separated. Two minus signs here tell us we know we have two hyperbolas because we have minus x squared plus y squared equals 1 and y squared minus z squared equals 1. Each of those, in those planes, those give us hyperbolas. And the two minus signs tell us we have two sheets. So let's talk about how we would sketch this one if we wanted to sketch this surface. So I want to draw my axes here. I'll extend my y here and my x back here. So in the xy plane, when z equals 0, I have minus x squared plus y squared equals 1. And this is, if I switch this around, just write it in more familiar form, y squared minus x squared equals 1. That's a hyperbola, and its axis is the y-axis. So in xy plane we get this hyperbola with its axis on the y-axis. And we get one back here because we get hyperbolas give us 2. And then in the yz plane, when x is 0, I have y squared minus z squared equals 1. So that gives me a hyperbola in the yz plane. Let me do something here. YZ plane. And its axis is its axis is the y-axis again. So I get this hyperbola now of, put this one in red, so it kind of goes up, above, and down below, up above, and down below. And then to see that we don't have anything in the xz plane, to convince ourselves we don't have anything that connects these two. In the xz plane, I have minus x squared plus, or minus z squared equals 1. Well, can I have a negative? X squared is always positive. Z squared is always positive. I have a negative minus something else gives me a positive 1. Is that possible? We're subtracting two positive numbers and getting positive 1, or two negative numbers and getting positive 1. So that on the real number system, this isn't going to work. So this is impossible. So there's no trace in the xz plane. So that tells us there's no trace in the xz plane, so it doesn't touch this plane. And then to go a little further, if y is greater than 1, in each of these, if y is greater than 1, we get circles parallel to the xz plane. So I connect these shapes here with little circles to get my hyperboloid of two sheets. So I get two kind of hyperbolic shaped dishes that are faced away from each other. So in cylindrical coordinates, this is a hyperboloid of two sheets. Rectangular coordinates for this one, maybe a little easier to work with. All right, so these surfaces, we'll keep working with them a little bit here, a little bit there, until we get more and more familiar with them. Questions? Questions on conversions? Conversion's not too bad. I think sketching the surfaces can be challenging, just to figure out what the shape is. But we'll keep practicing, keep having little sips of Tranya, so we start liking it more and more. And then all of us will be laughing like Balak. All right. And I know I keep saying it, but it is true. When we finally start getting to put surfaces and vectors together, that's when things get really, really nice.